So why is transition important? That is, this transition from laminar to turbulent flow. Well, first of all, is heat transfer problems, survival, and for reentry vehicles. The key point is that if you know where transition is going to occur, at what altitude it's going to occur, the temperature time history of your system can be more or less calculated. And this is something that we were doing at Sandia over 40 years ago. And but the big unknown was, where does transition occur? And so that's the big driver in looking at any sort of reentry vehicle or high-speed flight situation. There's also fuel savings having to do with laminar flow technology, which applies to transports. Excuse me just a second. Which is also very important. So how do you get inspired by looking at transition? Well, everyone's been to a Chinese restaurant. And so this was one fortune cookie that I got. Since if there's no wind, there'll be no waves. And another one is go with the flow and make your transition ever so much easier. So this is the kind of thing you look for when you go out to eat. Now, a model for low-speed transition would look something like this. A little bit of a tutorial. Upstream of your particular model, you've got turbulence, which is vorticity. You have sound, which is an irrotational field. And you've got particles. All of these three things will enter the boundary layer and cause some sort of a disturbance that eventually leads to regular waves in a linear regime. Things go nonlinear. There's a breakdown region where you get a number of different interactions, and then finally turbulence. It's a little different in the high-speed case. This is a slide that I know John Schmischer doesn't like, but we have to live with it. John?
I'm just throwing on it.
You have the same situation before. You've got vorticity, sound, and particles, but now you also have temperature fluctuations, temperature spots, entropy spots they're called. They enter the boundary layer in a region called receptivity. Now, receptivity is the mechanism by which free stream disturbances enter the boundary layer and cause the initial conditions for unstable waves. They can interact with the nose bluntness, surface chemistry, roughness, and you can get a number of different things. At small angles of attack, you can get transient growth. At large angles of attack, you can get crossflow. So different kinds of mechanisms will present themselves. Now, from the theoretical side and computational side, we can do the whole span from theory in DNS to parabolized stability equations, to DNS again, to large eddy simulation in the turbulent region. And so computationally, things can be handled very well. It's the experimental side that offers the most challenges. With that, not only understanding the mechanism for transition, but then the most important thing is the control. And that's usually in this particular region here. And then there's gas chemistry that we have to take into account as well, although I've got some new comments to make on that. So this, if we look at transition prediction schemes, a good friend of mine, Dan Rita, says there are three ways to predict transition. T leaves or chicken endrals, or RA theta over edge Mach number. That's momentum thickness Reynolds number over Mach number. Physics-based engineering correlation derived from high-quality experimental data, that is some REKK critical, or numerical predictions based on first principles. Well, First of all, I think Reynolds number correlations are not physics-based, but rather they're something else. They're just correlations, and they are susceptible to failure. My transition prediction scheme is as follows, that we don't have it yet, but it's just beyond the horizon, okay? Then if you look up the definition of horizon, it's an imaginary line that continues to recede. Okay, that's what we're up against. But what do we want? Okay, if I look at this pyramid, the first thing you get is data acquisition. You get a bunch of numbers, and you can do some processing, data processing, and get information. So you can get information here, but still you don't know anything. From the information, you can create knowledge, but it's only after you've created the knowledge that you can get wisdom. And there's a big difference between wisdom and knowledge, and I think what we're really seeking is the wisdom of transition prediction. So how do you get wisdom from knowledge? Well, first of all, knowledge, you have to know the difference. Knowledge is knowing that tomatoes are fruit. Okay, everyone knows that. But wisdom is knowing not to put it in a fruit salad. And this particular quote dates back to the 17th century when Gregor Mendel was doing his genetic studies. And this was on the entrance to the Abbey of St. Thomas, in Latin, of course, but that says from knowledge to wisdom. So that's what we really want, is wisdom. So if we look at some of these other ideas that are out there, there are a number of people that have made direct quotes, and I've checked on those quotes. And Dan Rita says there's an infinite number of combinations of flow field parameters and an infinite number of roughness parameters that determine transition. So there's no universal criterion for transition. That's true. That's knowledge. Some people just say it's too complicated to be solved. So when you look at those two sketches that I put on the board where you've got particles, temperature, vorticity, sound coming into the boundary layer, it's a 4-parameter space plus the surface conditions, so you just can get overwhelmed by all the possibilities of what can happen. So the main thing is, if you take this approach, this is just knowledge, it's not wisdom. You're not going to get anywhere. But the real theme is that as the tools improve, we have to extend the ideas to vehicle applications and transition prediction. Now, Deepak Bose said, though, that as far as NASA is concerned, they're not hopeful that a reliable transition prediction tool would be available. So, faced with this kind of opposition, it's hard actually to look at some fundamentals with regard to transition. But you can do something. A physics-based approach is where you integrate theory, computations, experiment, and control, not just rely on numerics. Look at initial conditions, surface conditions, thermochemistry, and validate codes with experiments. So when you do that, the goal is to understand the sensitivities and impact of known unknowns and lay the foundation for reducing the function space of unknown environmental inputs. That's the unknown unknowns. To give you an example, as part of the one of the conclusions that came out of the National Center for Transition Research was that thermochemistry is not so important for transition. So that really removes one of the major stumbling blocks, and it's a tremendous simplification of the problem to be able to say, yeah, chemistry is not so important as some of these other items. So that's part of the physics-based research, is to understand that some of these initial conditions are not so important as other initial conditions. And you can then winnow things out in such a way that you can get a grasp on the problem. Now, I was introduced to boundary layer transition on reentry vehicles in 1972 at Sandia Labs, when we had a vehicle that came in almost laminar. And they say, oh, we get this guy Saric, he does stability work, he should be able to do that. But I really never worked in transition before. And so I looked at a basic physics approach, and then also looked at a utilitarian approach, trying to do correlations and things of that sort. And what was available at the time was the Markovan roadmap. Now, don't try to understand this or even read it, but here's where you take an example of one of the naysayers, as I mentioned earlier, of saying this problem is too complicated to be solved, in that you try to include all the different effects that could occur, and then you could just get swamped by the details and never make any progress. So if you try to look at a utilitarian approach, these are the RE theta over M correlation techniques. They're really a threat to utility. NSF used to have this idea, I think since discarded, of doing practical research, okay? And that is only develop tools with existing technology that are needed for today's problems. And in fact, if you do that, then the future generations are deprived of the basic tools that they need to solve their problems. So that's the fundamental justification for basic research, is that you're really looking 10, 20 years downstream. And so this need for fundamentals is still something that faces transition research today. So there are really two strategies then, and you have to work them together, because somebody's got to pay the bills, and there are practical problems that have to be solved, and you still have to address the fundamental issues. So there's designer tools, and there's a list of old saws. I'll explain this in a little bit. There's Reynolds number correlations, there's transition altitude correlation. Give you an example, RE theta over M is nothing more than an altitude correlation. When I was back at Sandia, we just used transition altitude as a criterion, but you can fancy it up and look at momentum thickness, Reynolds number, but it's all the same thing. It's still a transition criterion, altitude criterion. But the topic of the seminar is really going to look at basic mechanisms and how they fall in line with some of these old ideas that have been around for a long time. So here's some old saws that are efforts at correlations in basic physics. And a saw is really an old English word. It comes out of one possible definition is a saying discredited through long repetition. And so it's an old, I don't want to say old wives' tale, that's not proper anymore, but it's an old tale that is not considered reputable. So one of them, and this was one of the first that I was introduced to, is to look at the minimum critical Reynolds number. That is a Reynolds number below which all disturbances are damped. And people did that because computers were small and that was all you can calculate. And but on the other hand, changes in critical Reynolds number can be opposite to the actual growth of the disturbances. And total growth and fetch are more important than changes in the minimum critical Reynolds number. So this has been discarded for some time. Nonlinear near the neutral point, so-called Stewart-Watson method. There's probably, I haven't counted them all, but probably at least 100 JFM papers doing Stewart-Watson method for nonlinear stability, But the small parameter is the Reynolds number minus the minimum critical Reynolds number. And it's at a point in the flow that it has absolutely no meaning. It has nothing to do with transition. But nevertheless, you can still publish, but it's really not of any practical interest. And the people also did 2D nonlinear of one wave, and the problem is there's nothing in transition that's two-dimensional. Everything is three-dimensional, and that's the zeroth order problem, not the next problem after two-dimensional. Oh, occasionally this still crops up that two-dimensional is most unstable. This is Squires' theorem. It's really been misinterpreted quite a bit. And it's only with regard to the minimum critical Reynolds number, which we've already said that it's not important. And so 2D is not always the most unstable wave. People use Reynolds numbers based on displacement thickness and momentum thickness, but all that means is that there's a Reynolds number, there's a constant in front of the square root of the X Reynolds number. And why not just use the square root of the X Reynolds number? Leslie Mack was probably the first one to introduce this, and but you'll still see people use RE delta star and RE theta to measure stability behavior, but there's no particular reason. It just confuses the issue. There's no basic physics that comes out of using either one of these. There was an idea that you had a snap-through transition in plane quasi-flow, but when you looked at it very carefully, plane quasi-flow, channel flow, showed that it was really TS-like, spatially growing waves, just like in a boundary layer. This is about the time I got involved in experiments because nobody was doing experiments. And one of the other things is that, and you'll still see this, that transitions can occur at a U prime max of 1% of the free stream velocity. It's sort of an amplitude criterion. Well, it turns out if you have a subharmonic breakdown, this can break down at amplitudes at about 0.3% of the edge velocity. And if you're careful enough, and we did this in the laboratory, you could generate linear TS waves at 3% amplitude and not see transition. That is, things that satisfy the Orr-Sommerfeld equation look very similar to linear behavior, and yet it's still a laminar flow. So this has no real meaning at all as an amplitude criterion. Okay, I mentioned earlier correlate with RE theta over M. This is just an altitude criterion. I'm doing this out of order for a purpose, and you'll see in a minute. You can correlate with unit Reynolds number. Back in the days of high-speed flow and noisy wind tunnels, people were actually seeing effects of the unit Reynolds number on transition. But this really can never be true. There's some missing length scale in the problem. And it's determining that length scale, whether it's a sound radiated from the sidewall boundary layers, surface roughness, or something of that sort that gives you a Reynolds number. For crossflow problems, that is problems on a swept wing, people correlate with the crossflow Reynolds number. This is easy to calculate, but it doesn't work, unfortunately. And it's about all you can say. And then there's the correlation with e to the 9th or e to the n. And this works if the initial conditions are the same, and it works with TS but doesn't work for crossflow. But anyway, this is some progress, okay? This is something to look forward to, and I'll spend a minute. This is suggested by Amo Smith and Jan van Engen simultaneously in different parts of the world. in 1958. The basic idea is that the linear growth extends over long distances. Breakdown occurs over short distances, that is in subsonic flows. So use the linear growth to correlate transition. And basically what you do is if you define a spatial growth rate as sigma and A over A naught as an amplitude ratio between two spatial positions, then stability theory gives you A over A naught as some E to the integrated growth rate. And that's where you get E to the N. So N is nothing more than the integrated growth rate for between 2 points in the boundary layer. And it's the log of the amplitude ratio. And so people correlate transition with this so-called N factor. But I want to point out that only if the initial conditions are the same. That is, in fact, I'll do that on the next slide. N is calculated from one set of data and used to predict transition for another case. And then environmental disturbances must be the same in both cases. Geometry must be similar. What I mean by similar in this case, they don't have to be exactly the same. But if you can talk about airfoils, swept airfoils, and they can have different pressure gradients and things of that sort, which is okay. But you can't compare cones with the swept airfoil. And for low-speed flows, in flight, is N factor of 9 is not too bad. And so sometimes it's just called the E to the 9th criterion. But there's a lot of scatter, especially in high-speed flow. So if you violate either one of these conditions here, the environmental disturbances or the geometry, sometimes you'll get 4, and sometimes you get 14. And there's always a big scatter, so you can't rely on that particular number and just be kind of guided by it, but you can't look at it religiously. So what I've devised is a way to calculate the N factor. And what you do is you take a set of dice and you take the one spot and you put 6 more spots on it. So the number of spots vary from 2 to 7 instead of 1 to 6. So the centered probability in this case is 9. And sometimes you get 4, sometimes you get 14. Saves a lot of computer time. So another correlation technique which offers some promise and in some restricted regimes actually works is to correlate with REKK. This is a notation that Dan Rita came up with. It makes a lot more sense than REK. And the definition is as follows. REKK is the density times the velocity evaluated at the height of the roughness element divided times the roughness element height divided by the viscosity. Whereas REK then is just the free stream conditions or edge conditions multiplied by the roughness height divided by the viscosity. So this REK note that this is of order K, and it may be better in some cases. It depends upon the amplitude. When you've got linear receptivity versus nonlinear receptivity, then you have to vary linearly with the roughness height. And so REK maybe make a lot more sense than REKK. So in this case, if the roughness height is on the order of 1% of the displacement thickness, typically the receptivity is linear. But as you continue to increase the height, it actually can go as K to the 4th for roughness heights on the order of the displacement thickness. So there's a whole range of variables here for roughness height that you have to include. And the mechanisms change as well. So you can go from linearly excited TS waves to transient growth just by the height of your roughness element. Another old saw is that quiet tunnels are necessary for transition. Since I have a quiet tunnel, I shouldn't be saying this, but perhaps only when TS and second mode are the principal mechanisms. That is, streamwise instabilities or acoustic modes are the principal mechanisms. We found that crossflow and Gertler instabilities, this is surface curvature, are relatively insensitive to sound. And so you can use noisy tunnels, especially true in high-speed tunnels, very effectively if you're looking at crossflow or you're looking at Gertler type problems. The reason is the free stream vorticity is strongly stretched when you begin to expand above Mach 2, and vorticity doesn't play a very big role in that case. And so transition itself is probably insensitive to noise in a tunnel if you're looking at the proper mechanisms. So crossflow and Gertler are candidates for conventional wind tunnels. And that's something to keep in mind when you're choosing the problem in your wind tunnel. There's another school of thought that says, see, what quiet tunnels do, quiet hypersonic tunnels, is that you suck off the boundary layer prior to the throat, and you start a new laminar boundary layer over a polished throat. And so there's some bleed valves involved where you suck off that boundary layer. If you turn the bleed valves off, you'll actually trip the flow. And some people seem to think that quiet tunnels mimic conventional tunnels when bleed valves are closed. This is not exactly true because the two quiet tunnels that are in existence, mine at Texas A&M and Steve Schneider's at Purdue, when you close the bleed valves, the fluctuation levels are on the order of 3 to 5%. This is on P prime total. And conventional tunnels, though, operate in the range of 1-2%. Depends on the unit Reynolds number, of course, but ordinary conventional tunnels perform much better than quiet tunnels with the bleed valves closed. And the reason is you can't start off designing a high-speed wind tunnel with a forward-facing step at the throat. It just doesn't make sense. Nobody would do that. I mean, there's no good reason to do it, but that's exactly what you do when you close the bleed valves. Is you have a forward-facing step where you're sucking off the boundary layer, and you're fixing that, and so it looks like a forward-facing step. And so it can't possibly be the same. So right now we have to keep an open mind on this because there's still some people that believe that you can close the bleed valves and mimic conventional tunnels. Now, final correlation technique is to correlate detachment line contamination and stability with R bar or RE theta, that's momentum thickness, Reynolds number on the attachment line. I haven't said much about this, but when you take a swept wing, the attachment line is a separating flow field line, and the flow along that attachment line is not zero. It's not a stagnation line, but it's an attachment line, and the flow separates. And so what happens if that flow goes turbulent somehow, then that feeds right into the boundary layer, and all bets are off in that case. Well, this is a success story because it works at all Mach numbers. That is, if I have an attachment line, if I think I've got an attachment line problem, the momentum thickness Reynolds number depends upon the unit Reynolds number, of course. and also depends upon square root of the unit Reynolds number. It also depends on the square root of the nose radius. And so all I have to do is control the nose radius on my leading edge of my swept wing, and I can eliminate this attachment line contamination or attachment line stability. And so it's an easy design tool, and it's something that's been effective. And there's other ways of doing this, so-called gaster bumps or little suction patches or things of that sort. But it is possible to correlate attachment line contamination with this, and it applies both subsonic and supersonic flows. So it's not all grim, but it's a result of doing very careful experiments and in both low speed and high speed flows. Okay, so let's now get into the fundamental approach to turbulence. And this is a roadmap. This is the simplest roadmap that you could devise. Up on top here, I've got forcing environmental disturbances. If I move from left to right, the amplitude is increasing. And as the amplitude increases, I move along this receptivity section. Now, for low disturbance environments such as flight, it's possible actually to go through and look at just excitation, receptivity and excitation of the primary modes. These are the so-called eigenmodes of the Orr-Sommerfeld equation. And from there, secondary mechanisms and then breakdown of turbulence. This is a very popular way of doing stuff computationally or analytically. However, as the environmental disturbances increase, either in free stream turbulence or in surface roughness, you get something called transient growth, which I'll explain in just a second. And transient growth can either interact with the primary modes and then secondary mechanisms. If it's large enough, it can actually avoid the primary modes and go right to secondary mechanisms. Or it can in fact lead to a bypass. Now, the definition of a bypass transition has changed over the years, and except for what bypass originally meant and means now, is that it bypasses our state of knowledge. So it's possible actually, let's say for example in turbine engines, transition on the blades of a turbine engine is a very high disturbance environment. And there's nothing like it in the world, and we don't know what's going on in that case. And that's a case of a bypass. You don't see any primary mode, secondary mechanisms or anything like this. It just goes right to breakdown. Sometimes you'll see transient growth being called a bypass mechanism, but in fact, you can calculate transient growth modes and indicate whether you can get transition or large disturbance growth due to transient growth. And this is now done routinely. So which path you take here depends upon the forcing environmental disturbances ultimately and the surface conditions. So prior to 1980, it was really only the Klebanov, Tidstrom, and Sargent experiments and about 12 incorrect theories to try to explain those. But then over the succeeding 16 years, this is for low speed flow now, in low speed wind tunnel, low turbulence, low speed wind tunnel. We've studied the receptivity problem, and it was done with analysis, DNS, and experiments. This is all summarized in an annual review paper written some years ago. And we looked at leading edge sound, leading edge turbulence, 2D roughness and sound, 3D roughness. The same sort of people are involved in all these problems. So we made start on the receptivity problem and getting initial conditions for unstable waves. However, as far as stability and transition goes, we've also been developing these non-parallel and parabolic effects. This is pioneered by Torvald Herbert. We did work on subharmonic breakdown. E to the N method was now given a civilized treatment in an annual review article 20 years ago. And control is well understood. And control in this case means dealing with the linear part of the disturbance environment and controlling that before it leads to breakdown. But it's taken really until this paper here in 1996, about 16 years, to come up with something that you can hang your hat on. I mentioned transient growth. Now, the Orr-Sommerfeld equation, which is the eigenvalue problem for linear disturbances in a boundary layer, is not self-adjoint. And what that means is that the eigenmodes to the Orr-Sommerfeld equation are not orthogonal. So here's a case of two orthogonal vectors that can interact. And in both cases, the vector v1 and the vector v2 are damped, so that these are sometimes called the square modes. And they were ignored. They were ignored for generations, actually, because people say, oh, these things are all damped, they can't possibly influence transition. But look what happens if the vector v1 is highly damped, really highly damped, and v2 is only weakly damped. The resultant vector is one that actually grows. That is, v1 grows down to here, v2 not grows, decays down to here, v2 decays down to here, but the sum of those two vectors is really an increase. So you'll always get an increase in the amplitude and then eventually a decay. So if things are done properly, if the initial conditions are proper, you can actually get enough growth here, going from here to trip the boundary layer. You don't necessarily need Orr-Sommerfeld modes. You can take streamwise vorticity of one type or another that comes off a roughness element or as part of the environmental conditions. Any sort of three-dimensional modes can have this particular character. And then if they're not orthogonal, they're vector sums and can undergo transient growth. This is a development that's occurred only in the last 20 years or so. Well, maybe a little less, but and with regard to transient growth, people have looked at optimal disturbances. That is, what's the worst type of disturbances in that. They explained the blunt body paradox. That is, the early reentry vehicles were nothing more than heat sinks, spherical heat sinks, and it was thought that the accelerated pressure gradient on a sphere would keep the boundary layer stable. But you couldn't get any of these things to reenter successfully. They all burned up. And the reason is, and it was called the blunt body paradox because you couldn't tie any physics to it. But Tuman and Rashotko did a transient growth analysis of this and showed that in fact it's transient growth that can trip transition and explain early transition on reentry vehicles that you would think otherwise were stable. Rashotko also looked at some pipe flow data, old pipe flow data obviously, and showed that in fact the circular quasi-flow that is flow in a pipe has no linear stability limit. That is, it's stable to linear disturbances, period. So why do you get transition in a pipe flow? And what happens is that you get stable disturbances that interact, 3D disturbances that interact, that could create transient disturbances. Now, these occur only in modest to high turbulence. This is either in boundary layers or even in pipe flow. If you're very careful with your pipe flow, you can actually get Reynolds numbers of up to 50 million or so, which is far exceeds the usual 2,300 for Reynolds number. And then you can carry this out with some careful experiments done by Ed White on discrete and discrete periodic roughness. And here we find that the receptivity for transient growth is, due to surface conditions, is on the order of k to the fourth, not k squared or k, but it's highly nonlinear and much higher, stronger function of the roughness height. We're extending this to hypersonic flows, but the program got cut, not by the Air Force, but by NASA. And so this was never really completed in the hypersonic flow. Somebody has to go back and readdress this transient growth in hypersonic flows again. Another example of transient growth, this is so-called Klebanoff-Titchem-Sargent experiment, where you get, this is a smoke flow visualization where you get these two-dimensional waves that get a three-dimensional crinkle that form these lambda vortices, and eventually you get breakdown. Well, the span-wise wave number for these vortices are on the order of 0.5. People wonder where you got the initial conditions for that. Well, that 0.5 is actually the optimal wave number for transient growth for a Blasius boundary layer. And so there's a connection now. Again, the transient growth is modifying the three-dimensional nature of the disturbance environment. So that was just mostly three-dimensional boundary layers. If we go to three-dimensional boundary layers, prior to 1988, we knew that traveling cross-flow waves were more unstable than stationary waves. So everybody was ignoring stationary waves and coming up with different methods for looking at the stability, looking at an envelope method or direction of growth and things of that sort that are strongly three-dimensional. But the early swept flat plate experiments, this was a experiment that I did with one of my students, and then followed up by Bippus and Kachanov, where we created a crossflow. We found out that the surface roughness had a strong sensitivity. That was all we saw experimentally in a low turbulence environment was stationary waves, not traveling waves. So the only time you saw traveling waves was if the free stream turbulence was increased to such a level that provided initial conditions for the traveling wave. But if you're in a low disturbance environment characteristic of flight, all you saw were stationary waves. So again, on the topic of three-dimensional boundary layers, we looked at receptivity from about 1988 to 1998, the role of surface roughness. Now, surface roughness in this case, we're talking about is micron size roughness. That is 5 or 6 micron roughness causing transition to occur. This is unheard of, but nevertheless, this three-dimensional boundary layer characteristic of swept wings is very sensitive to surface roughness. We also looked at the role of free stream turbulence in sound. This free stream turbulence was done principally by Hans Bippus, and he showed that if you increase this turbulence level, as I said just a minute ago, then the spectrum changed from stationary waves to traveling waves, but it had to be on the order of an order of magnitude higher than most quiet tunnels. And for sound, we found that we broadcast sound levels of 130 decibels into the wind tunnel at every imaginable frequency and broadband, single frequency, et cetera, et cetera. And we approached the noise levels in the New York subway and had no effect on transition. And so this was another, this is another big deal. This is part of separating this wide spectrum of things that can go wrong or cause transition by narrowing it down to a smaller parameter space and getting to understand what was going on. But it took 10 years to do that. We also looked at stationary waves and their harmonics. We looked at early nonlinear behavior and did validation experiments for nonlinear parabolized stability equations and DNS. This is all summarized in another annual review article a few years ago. As a result of that, well, we're running out of time, so let me just jump to this next slide. This is a series of contour plots. These are velocity contours, iso velocity contours in a three-dimensional boundary layer. The bottom is the computations, the top is the experiments. And they show that this is the slow rollover of that cross-flow vortex that convex order 1 momentum in the boundary layer. Even though that vortex itself is very weak, it convex order 1 momentum and eventually rolls over to such an extent that you get low momentum fluid on top of high momentum fluid, which causes inflection points and then is subject to secondary instabilities. And that's the breakdown mechanism. But just to show you how far we advanced, again, the comparisons between these two are rather remarkable. This is a nonlinear parabolized stability equation computation, and that's the experiment.
Who did that bottom calculation?
Helen Reed and her team of students. We were working side by side. We're actually married.
Which came first?
Pardon? What came first? I think the marriage came first.
So you consider that good agreement then?
We're talking about
She's not here, so.
We're talking about a nonlinear saturation problem that linear theory doesn't cover. Linear or Sommerfeld equation, if you look at this as n factor versus position on the wing, this is the ordinary or Sommerfeld equation, which is considered the Bible, okay? And it's way off from the experiments. It's the blue line right there. The experiments show that the amplitude increases and then saturates before it goes to transition. If you did a linear parabolized stability equation, it follows everything up to the point of it going nonlinear, and then whereas the experiments heel over and the linear continues to grow, then the nonlinear predicted the saturation. Yeah, I think that's darn good agreement. I mean, so we looked at that secondary instability. That is where you get these multiple inflection points. And over a 10-year period, we finally nailed the secondary instability with both theory, DNS, and experiments. And showed that there are two modes of high frequency breakdown. And because there's two inflection points in that velocity profile, And if I can go back right here, there's an inflection point in this direction. That is a DUDY having an extremum in this case, but there's also one in this case, a DUDZ, and it's actually the DUDZ that triggers first. And then there was control, span-wise periodic discrete roughness elements. And this is the talk for this afternoon, and so I'll delay discussing that, but the idea is to introduce roughness in a boundary layer, excite some linearly stable modes that will stabilize the boundary layer. So for those hanging around for this afternoon's lecture can hear that. Effective curvature, again, prior to 1978, there was even confusion regarding what equations you have to solve to get stability of a flow over a concave surface. The mechanism was known, but the actual way of calculating it for boundary layers was not known. And so we did a rational formulation of stability equations, got the classical linear solutions, but Phil Hall really started developing parabolized linear solutions, and this was the key answer because the flow is parabolic in this sense, not elliptic. And then this was carried out to do nonlinear parabolized Navier-Stokes with variable curvature and convex curvature, which you can't do with linear analysis at all. This is all summarized in an annual review article in 1994. But again, look at the time scale over which that took place. We need a hypersonic Gertler analysis. If you go to the Smithsonian Institute and look at some of those reentry vehicles, you see there's different ablation rates between the nose cone and the heat shield. And so there's a region of concave flow after the nose cone. And so you'll see longitudinal striations burned in on the surface of the heat shield, which is due to Gertler vortices. And so this is a problem in hypersonic flows. This work is in progress, not experimentally, but computationally using nonlinear parabolized stability equations. So note the 10-year time span on previous topics. So how many in this room can raise their hand to say that they fund 10-year research programs? Well, that's extraordinary. I mean, start to finish 10 years?
Yes.
Yeah, that's pretty good.
How many program managers did you go through in your crossbow work? Michael?
5.
Father, me.
Yeah, 5 program managers. Most of which wound up at ONR. Ken Iwanski, I found out, is now at ONR. He funded some of my original AFRL work when he was at AFRL. And so it takes a while because you're working on a 2-year time scale or a 3-year time scale, but you have to show results and progress, and it's sometimes very difficult. Okay, if I can hold you for another 5 minutes or so, what I want to do is just talk about some fundamental understanding of transition come from canonical experiments, and looking at this regime in here and showing what can be done. One of them is the Gaster wave packet. Klebanov type breakdown and a Vignansky turbulent spot. And by looking at these things in hypersonic flows, there's a promise of getting something done. Just to give you some quick pictures, that the understanding of the stability is really coming in, used to come from canonical experiments, but now they're going to be coming from the DNS and guiding the experimental results. Let me skip through some of these and just come to my message. I needed the hour and a half for this talk, not the one in the afternoon.
You can continue.
Okay,
We have the rooms. People need to leave the temperature.
yeah, but the ability of the mind to absorb is limited by what the seat can endure. So let me just go through the messages. Laminar flow control works in the linear regime. We don't need the details of transition, only the causes. And this is really something that's important. We need something clever for roughness control, but for almost anything else, we can use linear theory for laminar flow control. That is, get disturbances while they're still linear and try to damp them out before they go nonlinear. Once they go nonlinear, it's a much more difficult problem. The so-called second mode or MAC mode or acoustic mode, they're all the same thing. We've had unambiguous observations in the two quiet tunnels that exist. You can control these with ultrasonic coatings, done first with fundamentals by Norm Malmuth and Sasha Fedorov. And then Hans Horning did some experiments in T5 at Caltech to demonstrate control for hypersonic instability modes. Receptivity, we've done work computationally on entropy spots. Sound through a shock layer turns out to develop vorticity. So you can't ignore vorticity all the time when you've got a shock layer. And also looked at receptivity control for 2D roughness, again, because this acoustic mode is a 2D mode. So there's been a lot of work on chemistry and chemistry modeling with stability, and you can efficiently extend this to nonlinear, and the conclusion when it's all done is that chemistry is not too important. It's not the principal thing that you have to look for in transition of turbulence. What is important? Vorticity, sound, and particles. Transition's an initial value problem, not an eigenvalue problem, but it's like the drunk looking for his wallet under the streetlight. When asked what he's doing, he says, I'm looking for my wallet. But the fellow who asked the question said, obviously it's not here. I probably lost it over there somewhere, in the dark. And the fellow says, well, why are you looking here? He said, well, that's where the light's at. Now, we've been looking at this as an eigenvalue problem because that's where the light is at, but it's not an eigenvalue problem, it's an initial value problem. It's the initial conditions that dictate transition, and any ultimate transition prediction scheme has to be treated as an initial value problem. We've just waited too long on this. Finally, wisdom is not found overnight. Some years ago, I said to somebody in this room, give me 10 million over 5 years and I think we can make some progress. So I think I was off by a factor of 2 in both the money and the time scale. But that's what we're looking for. Then finally, it's just beyond the horizon thing. There's real job security here. Okay, thank you very much for your attention.